Okay, in our second exception here for integration by parts, where we choose u to be the part that differentiates to 0, we have a situation where neither part differentiates to 0. And in this case, we have to go through a different process. I'm going to give you a few little steps here for doing it, and then we'll go through some examples. I shouldn't say steps, but I'm going to give you the overall picture of what happens here. When you have this type of situation where neither part in your integral, which requires an integration by parts, can be differentiated to 0, and you don't have a natural log of x, what you're going to do here is you're going to perform integration by parts twice. This is going to give you back the same integral that you started with. Once you get to that point, you're going to use algebra to solve for the integration you are looking for, and then at the end, don't forget to add your plus c. Okay, and those are just kind of the overall steps that we're going to go through. I'm going to do a couple of examples, possibly in one video, maybe in two. We'll have to see how it goes. And so you can see how this process works. But again, the big picture we're going after there is we're going to perform that integration by parts twice, at which point we'll get back the integral we started with. Then we'll just use some basic algebra to solve for what we need, and then finally add that plus c on to the end. So let's try an example here. And we're going to look at how we know to use it, as well as how to use it. So let's start by looking at the integral of e to the x sine of x dx. And here's an example of what I'm talking about. Let's go through the process. First thing we try to do is try to fit a basic rule. And there are no basic rules that have an e to the x and a sine of x in them. Next, we would try a u substitution, but in that case, we need a u and a corresponding u prime, and we don't have that here. So what we're going to do is we're going to look at the integration by parts, because I do see that I have two separate and distinct parts that cannot be combined. But notice that neither part of this is going to differentiate to 0. No problem. We're still going to go through the process. What you pick for u makes no difference. But we're going to perform the integration by parts twice, so you want to stay consistent from one time to the next. In other words, if I let u be the exponential part, I need to do that the second time as well. So I'm going to let u be my e to the x, which means my dv is everything else. That is the sine of x dx. And then we go through the process. There's my u. Again, to find the du, we use the fact that du dx is just the derivative of u. The derivative of e to the x is e to the x, and then multiplying both sides by dx, I get that du is simply equal to e to the x dx. There are two of the parts we need. And finally, we need v, which is going to be the integral of our dv. So it's the integral of the sine of x with respect to x. And when I integrate that, I actually get minus the cosine of x. We've got to keep that straight here when we're doing this. So I started out with my integral e to the x sine of x dx, and I turned it, basically, if you look back here, you can see that this was the u and this was the dv. And if nothing else, you need to remember that this will be equal to uv minus the integral of v du. So let's go ahead and put those pieces in. I'm going to multiply my u times my v, which is going to give me a negative e to the x cosine of x minus the integral of v du. So it's minus the integral of a negative cosine of x e to the x dx. And now, before I go any further, let me just rewrite that and clean up all those extra negatives in there. This is going to give me a negative e to the x cosine of x. Those two negatives become a positive, and I'm going to put my e to the x in front since that's the way it started, and I'm going to have an e to the x cosine of x dx. Now at this point we have created a new integral, and this new integral that we create is going to require us to do an integration by parts a second time. Remember the last time we picked u to be the exponential part, so we're going to keep consistent with that and let u be equal to e to the x, which means dv has to be everything else. So the dv will be equal to the cosine of x dx. Based on that u, we can once again find du. Du dx is just the derivative of that, and then multiplying both sides by dx, I believe we still get that du is e to the x dx. Those are two of the parts we need. The only other part we need is our v, and we get that by integrating our dv, and the integral of a cosine of x with respect to x is actually equal to the sine of x. Positive. Remember, they switch places here. So let's go back up and grab what we had there. Remember, we started out with the integral of e to the x sine of x dx, and we got this one piece that came out, a negative e to the x cosine of x, and then we had plus our new integral, and this time we're adding, and remember what we're looking for is a uv minus the integral of v du. So let's put those parts in. U times v here is going to then give me e to the x sine of x, and then minus the integral of v du, which means minus the integral of, and let me write it this way, an e to the x sine of x dx. And I did that so that we could easily recognize that we do indeed get back to the same integral that we started with. So if we look at the overall picture here, we have completed the integration by parts twice, coming back to the same thing that we started with. Okay, so the next step here is actually to perform some algebra. I want to solve for this e to the x sine of x. So let me get them all on one side. I have a negative integral over here, so if I take that negative integral and I add it to both sides, then it should actually disappear from that right-hand side, because anytime I add and subtract the same quantity, it goes away. One of these integrals plus one of these integrals is going to give me two of these integrals. So I'll have 2 times the integral of e to the x sine of x dx will be equal to a minus e to the x cosine of x plus e to the x sine of x. And remember, I'm not solving for 2 times it, I'm solving for just the integral. So algebra says we would then divide each and every term by 2, or simply come in here and multiply each and every term by a 1/2. And that'll make that 2 go away. And so we get that our final answer here is the integral of e to the x sine of x dx will be equal to a negative 1/2 e to the x cosine of x plus 1/2 e to the x sine of x, and then don't forget your plus c. I'll use the next video to do a second example of this process.